Alright, so here we're going to be looking at volumes of revolution solids, and the way we're going to do that is by looking at the disk method. Let's see what that is. Well, actually, let's start with some other stuff. The area formula for a circle, that should be easy to, you should know that. That would be A area equals pi r squared. So if we have a radius of a circle, we'll be able to find out the area of that circle. And the idea behind the volume is to integrate a circle as it changes and gets a solid. We'll see. Alright, suppose we have a curve f of x, and it looks like this. Now we know, let's say, from A to B, we know that the area would be the integral. So we could write the area R of the region. I don't know if I want to call that R. So the area would be from A to B, and we would integrate whatever the function f of x was. So we'd have this, and that would give us this area right there. But if we wanted to find, suppose we want to find the volume. Well, if we were to rotate this, that's a rotation symbol, not a G. If we were to rotate this around the x-axis, it would spin, and we would get a solid. Hopefully you can see that. Also notice that this distance right here, that distance would be the radius. That would be the radius right there. So if we, well, this is what I'm talking about. If we were to rotate this around, it would look like that. We'd create a disk. Do you see that? We'd create a disk. And if we integrated that disk from A to B, we would get a solid. And let's see what the solid would look like. If we were rotating around the x-axis, the solid would look like, well, it has that, and it's like a vase or something, right? That's bad. Undo. That would be the solid that we would get from this, where this is all full. We could find the volume of that. There's a way to find the volume of that. So if we rotated, maybe I'll write that, if we rotated the area of this around the x-axis, if we revolved it around the x-axis, we'd get a volume of a solid. So if we rotated this area around the x-axis, then we would get the volume of a solid object, and that solid object would look like this. So if we had, you don't have to write this, but if we had some function that just looked like this, and we wanted to rotate the area about the x-axis, then we'd get like a cone-shaped thing, right? If we were to rotate that. You can write that if you want, but you don't have to. So that's what we're going to be looking at today. Volume of a disk will be rotating around the x-axis and even around the y-axis, and they'll give us volumes of solids. Notice here the area of this circle is just pi r squared, and if we wanted to integrate this, so let's take a look at that. I'm going to zoom in here. The area of that circle would have been pi r squared, right? However, notice that this distance r, that distance there, is just f of x. That's just the function f of x. You plug in whatever value this is, and f of x would give you this distance. So, let's see. If that distance, this distance would be f of x for whatever x value. So the area of that little disk would be pi times f of x squared, because f of x is this distance. Like, you plug in some x value and it gives you the y value. That y value is that distance right there. So, yeah, if we wanted the whole entire volume, we could integrate that area from A to B. So actually our integration formula, our formula to find the volume of a solid, is like this. Is the integral from A to B, well, not capital A to B, of pi times whatever function we have, f of x, squared, and with respect to x. There we go. That's our volume formula. And the way I think about it is f of x is the radius of one single disk. So, I mean, it helps me remember the formula. If I draw a disk like that, then I know that the formula would be pi r squared, because that's for the circle, and then I integrate it to get the volume. So that's what we have. There we go. Let's look at an example in this one. Maybe I'll do examples in a different video. Yeah, I think that.